ask the panelists to say a few quick words about themselves and what they do and what's their experience in materials, what's their experience in quantum computing, and we can get started after that. Maybe we'll start with Christian.
Yeah, thanks. So I actually have a PhD in quantum information theory and quantum computing, and I have worked in academic research in that field for about 10 years, and then worked for Xanadu Quantum Computing for a time, and then joined Covestro, which is a worldwide operating chemicals company, 4 years ago, and I'm now heading the high-performance and quantum computing team that is part of Covestro's digital R&D department. And yeah, I have a little sort of pet project on the side, which is I'm one of the founders of and running the Quantum Journal, which is the open access journal owned by the quantum computing research community.
Great, thank you very much. Daniel?
Hi, I'm Daniel, chemist by training, so I have a PhD in material science. Started my career as a researcher actually on the chase to make new materials for display chemicals for about 7 to 8 years. Switched then careers, went into management consulting, maybe in parallel or maybe following BCG. I was at McKinsey and also working on doing some pioneering work on quantum computing. After that I worked at BASF, which is a quite sizable chemical company out of Germany, on strategy, but also on quantum computing related topics. And these days, I'm co-founder and CEO of Kipu Quantum. So we are doing quantum computing algorithm solutions, not only for the chemical industry, but of course also relevant for that sector.
Thank you very much, Daniel. And Matt?
Sure, Matt Langione. I'm a partner at Boston Consulting Group, and I lead our quantum computing topic. We work with tech providers to help with strategy, business model, these sorts of things. We work with governments on national quantum strategies, investors on diligences, but the fastest growing part of our business is end users. And within that, materials use cases are really on the rise. So excited to join this panel and discuss what we've found with you.
Okay, great. So, so the way maybe we can get started is, I mean, there are potentially people here at different levels of expertise and understanding of the space. So I thought maybe the first thing to get started on is to just level set and understand and think about what would be the new materials potentially that a quantum computer would be able to give us if we had one, maybe if we had a capable machine in the NISQ era or a capable machine in the fault-tolerant era. Do we expect to design new materials, new processes? Can we think about some examples maybe of what those might be? So, so let's kick things off that way. Maybe Christian?
Yeah, sure. So, I mean, especially in the polymer space, which is what's most relevant for us, the amount of possibilities that you have in designing materials and changing their properties, making them recyclable, for example, or making them, I don't know, more resistant to fire, or making them lighter, harder, are virtually endless, because you can build polymers from a broad range of different monomers, and you can use additives of all sorts. And so exploring that space of possibility experimentally, something that we've been doing for decades, but you can only do so much. And accelerating this kind of exploration digitally has been very valuable, or is already working very well. The additional accuracy that we hope quantum computing will deliver for the kind of simulations we have to do there, really has the chance to make these digital simulations of materials much more important and much more valuable. But on top of that, I think it's also much more about, or another sort of second area where quantum computing and the simulations we can do with quantum computing really can make a difference, is not in changing the materials themselves, but also changing the processes with which we make these materials, and also with which we recycle these materials, for example. A big topic for our company is circular economy. So we really would like to use these technologies one day to make our materials more sustainable.
Great, great. Daniel, anything to add there?
I think he gave a very concise and comprehensive answer. So maybe to give some flavor, I did my PhD in a topic which was around finding new materials, but I would echo that this is only part of the equation. And I would say the chemical industry at large is really driven by the quest to become more sustainable, either by making the same stuff from the same feedstock with maybe less energy consumption, but also in particular finding ways, as Christian put it, being more circular, using maybe making the exact same material, but using another feedstock that is ideally recycled, bio-based, etc. So that's really the big key topic. Maybe one thing to add: a lot of the product development in chemistry is along the lines of formulated products. So there you have oftentimes, I don't know, a formulation that is meant to clean stuff, personal care products, etc., which is, I would say, also driven by, it's to a certain extent the quest to finding new ingredients, but maybe more so making better properties with maybe fewer chemicals, reducing certain things like biocides, but still having a skincare product that doesn't start to get moldy if you keep it in your bathroom cupboard for too long. So that's some of the flavor I see to that topic.
Great, great. I think that gives tangible examples like resistance to fire, as you said, weight maybe, or increasing the strength, reducing the weight, and then reducing the energy required to, or the raw materials required to produce something. So I think these are very tangible. And let me kind of jump over to Matt now. And I know, Matt, you've done a lot of work on predicting dollar impact, right? So these were the tangible examples of new materials, new processes. What do we expect the dollar impact would be in the industry?
Sure, sure. I mean, I think just to echo what's been covered, we've talked about net new materials. But then I think, Daniel, you were also hinting at the potential for, a broader set of synthetic routes for existing materials, which could reduce costs quite a lot. So when we see, if you think about the markets, therefore, that are impacted, you've got a $4.5 trillion annual materials market, which is massive. About a little less than 4 trillion of that is commodity materials. And for commodity materials, we're probably talking about, with the quantum impact, more the synthetic route use case. For specialty materials, which is say $600 or $700 billion, that's where that could be accelerated by quantum computing. And basically, you may ask, well, how are those specialty materials being discovered now? And there's obviously non-computational methods. Then there's computational methods. There's kind of the four popular, DFT, coupled cluster, et cetera. And these are ways of basically approximating the Schrodinger equation. But they make effectively, what I'll say in these sort of technical things will be generally true and precisely wrong, almost always. But these guys are here to correct me. But effectively, you have to make a set of assumptions. You have to ignore things like Coulomb interactions, et cetera. And the hope for quantum computing is that, of course, you can simulate larger systems, but also that you can do it more precisely. So some of the very big opportunities I think that have been explored so far have been things around battery development, et cetera. But we think that this is one of the biggest potential markets, like certainly a $50 to $100 billion market over time, with about half of that coming from the specialty chemicals, things like unit cells of batteries for electric vehicles, to also so, better synthetic routes for, some maybe simpler kinds of chemicals.
Great, great. Okay, so thank you very much for that. So this is kind of the future, right? So we discussed of where things potentially can go if we had these very capable devices. Unfortunately, the reality of today is that the devices are limited. So just wanted to hear from you and the panel here on what are some of the limiting factors that you're seeing today in the work that you're doing, and with the hardware, with the software. What are some of these limiting factors that prevent us from actually realizing that future today?
Yeah, so I mean, on the quantum side, I think we've heard today, or also yesterday, several times that like noise and qubit count are still issues that prevent us from using these devices productively. But we have similar issues also with classical compute today. So there are cases where these methods that were just already named, the precision they provide is just not enough to, for example, do an upscaling to a pilot plant or a production facility based on just computations. And that means then some lengthy lab trials still need to be done to, say, verify what has been predicted in computations. And so there's, I guess, two ways in which the methods can be inadequate for what we want to do. They can be either not accurate enough or they can be too slow. Mm-hmm. And so if you want to take an existing method like DFT and you are okay with the level of accuracy that method yields for the use cases you're interested in, you just want to make it faster, then probably actually quantum computing is maybe not the right way to go. And you would much rather want to use a GPU or a TPU to accelerate the classical implementation of that method, make it much faster, something you're also working on. Whereas in many cases, these methods have just fundamental limitations in the sort of the physics or chemistry they can capture. And there's the big hope that quantum computing will provide a sort of catch-all black box method that yields the right results for the right reasons over a broad range of different problems. And actually, quantum computing, to provide a value in chemical R&D, it doesn't need to be like better than every possible classical computational method out there. It's enough that it just yields better results sort of on average across the board, because we can't sort of, for every little use case that we want, like have an expert and like pick the right classical method and so on.
Right. So basically you concentrated on needing to develop better methods that provide more accurate results. And do you see, essentially we have this one method, VQE, right? Do you see that as a potential workhorse that's going to drive essentially development of new materials in the future?
Oh, we can have a long discussion on like what the problems are with VQE. And I'm very much with what Clemens from BI said earlier today, that very fundamental questions still need to be solved and answered there. So it's a bit funny because this like applying quantum computing to simulate quantum systems is like the most natural use case, and I very firmly believe that it's the first commercially viable application of quantum computing. Everything else will come afterwards. But even though that abstract idea is so compelling that it's a story everybody believes, there's still, and actually even probably more so than in optimization, there's still a lot of fundamental science to be done to learn how to do that optimally. Okay. And like really orders of magnitude in sort of compute time have been shaved off these resource estimates over the past years. And the big question is sort of how long are we going to see like one order of magnitude coming off these resource estimates every year? Because we will need a few more of these orders of magnitudes to come off, but it's not unbelievable that that will actually happen.
Right. Okay. So, yeah, maybe Daniel, I don't know if you want to add to that, and maybe also talk a little bit about the hardware. Are there limitations we see there, and kind of what are some of the limiting factors there on the hardware side?
I would say on the hardware side, I mean, roughly speaking, it's number and quality of qubits. I'm very happy to see that there are new, beyond the old concepts. I don't know, I remember when I've been with McKinsey, I started to put a summary together with leading hardware paradigms. One was missing that is now very dominant back then, neutral atoms. So there are new concepts coming up that seem to catch up very quickly. Still, number of qubits needs to be improved. Things like coherence time, to have essentially to allow for higher circuit depth algorithms to be executed on real hardware. That's coming essentially. Okay. But I'm happy to see that there is continuous progress and also multiple potential scenarios in which hardware improvements plus the fundamental algorithm work that is being done by many players in the field, including Kipu, is essentially going to make it.
Okay, great. And I'll ask the panel a little bit later maybe to venture like a forecast and timelines and things like that. But before we get there, I also wanted to maybe ask Matt, obviously we're hearing from these two representatives here how they're already engaging, right? Yeah. So do we see a lot of other materials companies engaging? And I guess the other question that might be more interesting is the materials industry and chemistry industry as a whole engaging at the same rate as, say, finance or, let's say, pharma or other industries are engaging in quantum computing? Are they lagging behind? Are they ahead maybe? Well, how do you see that?
Yeah, I think it's a good question, and it leads into something that I also wanted to mention. We talked about the algorithms and the hardware. One other challenge in materials science that's a little bit different than pharma in instructive ways is that pharma, partly because it's regulated and for various other reasons, has a very defined workflow and at least relatively large and comprehensive public data sets, whereas materials science is fairly desultory in the sense that, I talked about 4.5 trillion, but that's spread across all sorts of industries, right? And so you've got automotive players and energy players, et cetera. And so there's just less of a kind of ingoing kind of lingua franca to work from. Obviously, there are materials databases, but for those of us who've looked at those, they're fairly patchy, and they can, especially the public ones, can be particularly hard to use. So some of the experimentation itself requires a lot of non-computational work, to be honest, as well. There's the algorithms of the hardware. And so I think partly because of that, whenever you have a workflow that's a little bit less well-defined and a little bit more experimental in nature, first of all, you have less kind of copycatting. So there's it's hard to see, if Exxon invests in quantum, that doesn't mean that Ford will, right, necessarily, right? Because of course they don't even see themselves as competitors. So I think that materials, for a number of reasons, some of them are kind of practical, as I've mentioned, have been a little bit slow to adopt relative to your point, pharma and finance. And I think that it's, again, surprising and slightly disappointing, because as you say, I think that one of the earliest potential use cases is materials, and then also not just earliest, but if you think about the use cases in quantum, that for reasons that aren't economic necessarily or financial, or at least maybe indirectly so, are so exciting. Things like high efficiency solar panels, right, and other kind of sustainability and kind of climate use cases. A lot of those are in the materials space. I mean, even unit cells for electric vehicles, right, for batteries in electric vehicles. So all the more reason that while we do see some activity from players, especially in energy, it's something that I guess when we started this maybe 5 years ago, we would have predicted that they would have leapt out in front a little bit more so than they have.
Okay, and yeah, it seems that they're lagging a little bit behind. Okay,
Indeed.
Okay, yeah. So, but maybe so then this might be a good opportunity then to ask Christian and Daniel here, what's their expertise and what's their experience actually with what they've been doing, right? I guess for Christian at Covestro, for you, Daniel, now at Kipu, but before also at BASF. Could you give us maybe some of the examples of the work that you've been doing, and kind of what are some of the things that you've been experimenting with to kind of prepare yourself for the quantum computing future?
Yeah, sure. So for us, it's, I guess, if people see the kind of work we've been doing and publishing in scientific journals, and people will maybe think or feel that that's almost sort of academic research that we're doing. But for me, it's really about de-risking that technology. So I want to understand, I want to see through the hype. Yeah, I want to get a decent understanding of what's actually going to work, what can be expected to work, what the problems are. We think that with our partners, Ware, and we're also working with the Google Quantum AI team, together we have in some areas sort of unique combination of expertise where we can win some sort of small but the key battles, even with a small team, where we can figure out how to do things optimally and go beyond the state of the art and help push the field forward. And that, looks pretty academic, but it's actually there to answer pretty mundane business questions of when is this going to work, or what are the use cases, or these kind of things, or I don't know, there's this open research question like whether NISQ will provide quantum advantage or not. And I would like to be among the first to have a good understanding of whether this is happening or not. And we're not quite there yet, but working on it.
Great. Okay, Daniel?
Maybe to add to that, without repeating too much of what Christian said, all valid points, and I've seen a lot of that also at BASF, past employer. Something that always struck with me was a nice little quip from somebody I worked with at BASF, which is a very experienced theoretical chemist who saw essentially the full development over 20 years. And he used to say that the worst thing that could happen to BASF's quantum effort would be immediate quantum advantage, because it would essentially catch everybody off guard. And from that perspective, and I've seen this also at other companies, but BASF in particular is putting a lot of emphasis on building up capabilities in the quantum computing ecosystem. So this means not having one genius that knows it all essentially and could apply it everywhere, but kind of bringing this broadly into the organizations, having multiple stakeholders involved who could essentially look in this, and as well as also raising awareness throughout the organizations that people are actually aware that, of course, they are used to doing certain things, they kind of accept it into their daily routine, that certain stuff is just can only be modeled with coarse-grained methods, but this may change. So one example which really surprised me is battery chemistry again. So this is a huge opportunity which is oftentimes discussed. If you look at how this is done on a R&D scale, and this is not because BASF is lagging behind, I think it's one of the leading companies, the focus is a lot on automating workflows and kind of sampling through really quickly through a lot of different material classes. Reason for that is because it's very empiric workflows. It also takes very long because a new battery material needs to be demonstrated in a cell that is run for, I don't know, a couple of months. So people invest in automating that essentially. Mm-hmm. And if you ask why, the answer is essentially, yeah, you know, it's a solid material, we can't really model that. So people constructed whole workflows kind of trying to bypass the lack of a capability that, of course, is not here yet, but could be here with quantum computing in the future. And changing that is of course, going to take a lot of time.
Okay. So maybe we can take maybe one or two questions from the audience now, if there are any, and see if there are any topics that the audience wants to lead us to, and we can come back to some of the other questions. I don't know if there are any questions.
We have one up here. Let us get a microphone real quick.
Yeah.
I have heard today mornings in the talk given by Boehringer Ingelheim, that it takes about 3 days to calculate the ground state of a molecule in the pharma industry. Can you share this opinion? Have you experienced similar problems? Or is it specific for pharma because the molecules are so complicated?
Fairly well. I can comment on that because I think I know the paper fairly well. And the research estimates that were done there are sound, and they are, in terms of methods that were used, this is almost the state of the art. Like, there's very few additional optimizations that you could do on top of what they did that are known today. And yes, I think that highlights that a lot of more fundamental research is needed to actually make this dream come true of having high accuracy at high speeds.
And the same would apply to materials, or is there a fundamental difference between the drug discovery?
No, the molecules they looked at there as use cases, they are pretty representative also of the kind of molecules that would appear in a catalysis research study that we are doing. So that's pretty much transferable.
Thank you very much. We have one more question.
I mean, maybe if I can add one more thing. I mean, sure. Maybe there's one difference here is that I think there are cases where we would be very much willing to wait for 3 days or even 3 weeks for a result with an accuracy that is much higher than the accuracy of the methods we can afford today. Yeah. So maybe we are a bit more patient.
Maybe to add one comment there, I think, as you said, there are really tangible examples where people with classical methods are calculating much longer than 3 days. So I think the worst calculation I've seen was, I think it took like six or 7 weeks for a single molecule. We were technically also in the screening modes, but we essentially realized that the accuracy of the screening for electronics properties like color for certain materials was just way off. Mm-hmm. You could not get below a certain threshold in accuracy, and we were trying to figure out new methods to break through these kind of limitations. And then ultimately, I think it took like 6 to 7 weeks to calculate one single molecule.
Yeah, I think that's a defining characteristic of the materials industry, and also the pharma industry maybe as well, that people are not so much worried about sort of the speed of the calculation. They're willing to wait as long as they get an accurate result, right? So it's a little bit maybe different from optimization use cases or machine learning use cases, where maybe the speed of the calculation also plays an important role in the business case, right, and the business value. So there was one more question, yeah? Mm-hmm.
Here. Hello. Yeah. So we've seen a lot of quantum computing companies saying that they have their QPUs online. They may be faulty, small, but is there anything that your industry can already do with what's available, right? Maybe not doing the whole calculations, but speeding up certain little parts of the calculations. Can you comment on that?
So what's your view, Christian?
So, I mean, yeah, so these machines are online, some of them, and it can be interesting to use these machines for quantum algorithm development or for example, testing how well error mitigation techniques work. That's work that we've done in the past with Google. None of the machines that are online are sort of beyond classical compute in their capabilities. And so if you care about solving an actual real-world problem, you're always better off using classical compute today. Yeah? But then it's also clear that because of the scaling difference in these algorithms, there will be this crossover point. And yeah, it's a good idea to sit down for the use cases that are relevant for you to sort of figure out where that crossover point lies and whether that crossover point lies in a sort of reasonable time scale for the kind of problems you're interested in. And once we're past that crossover point, then I think the quantum advantage will sort of materialize very fast and very dramatically, yeah, because of this, in several cases, of exponential differences in scalings. But yeah, the way until this crossover point is a long and painful road, yeah, and we're still not there yet.
Yeah, maybe to add from again, Kipu is doing algorithms, so from that perspective, I think it's fair to say that there's no quantum advantage yet with the current machines, obviously, but it's still helpful for us to use the real machines because it allows us to demonstrate that the algorithms are actually getting more powerful, so that you require less circuit depth, or that you can solve ever so slightly bigger problems essentially on the same hardware. So that's an important yardstick. I would also say from our development workflows, oftentimes you see that algorithms run on simulated hardware behave better because it's an idealized scenario, and if you run them on real hardware, you oftentimes encounter problems that you would of course also encounter in similar fashion on 1,000,000 qubits or 10,000 qubits. So this helps us to kind of anticipate and essentially make sure that we don't develop algorithms that cannot be executed on the hardware that we will have in the next couple of years. So still valuable and important for us.
And I think from an enterprise perspective, taking back to your Bosch days, you made the comment that if all of a sudden there was a precipitous breakthrough, that would be a real challenge for Bosch. But certainly one mitigating activity that you could do is actually use these algorithms, right?
Yeah, exactly.
So very good question. Thank you very much for that. So I guess coming back to Matt, I wanted to ask this other fundamental question that maybe a lot of these materials companies might be thinking, which is, okay, why don't it's going to maybe take some time until we get there. Why don't I sit back, let maybe the leaders take the charge and invest money and do the research, the fundamental research, and then once Kipu comes back with their software package that can get the solution, can get it done, then I can just buy the solution and basically execute, right? So, so essentially be a fast follower, right? Not lead the charge, but be a fast follower. So, kind of, what's your perspective on that? I mean, is there a lot of risk there? Is there opportunity? How should the industry think about that?
Yeah, so I think that there's an enormous risk in waiting. And I've been on the record saying this for years now, and I'm going to say it again this afternoon. And we just published something today that says this. But very much so. The thing that we get oftentimes from energy companies, materials companies, maybe more than anyone, is we've never been particularly innovative. We've always waited and been a fast follower. And look where it's gotten us, and we're talking to mostly Fortune 500 companies, right? So then what's different this time? It's an argument that I've just become very, very accustomed to making. I think that the real differences here are that quantum computing is deeply, deeply talent constrained. If you don't have a serious quantum computing program, when quantum advantage happens, you're very unlikely to be able to attract the talent that would even start to get you an advantage in quantum computing. Another thing is that, quantum computing is one of the last redoubts of like good old-fashioned patenting. And so, you could actually have an IP advantage in advance of, quantum hardware maturing. And then lastly, I think that a lot of folks underestimate the difficulty and the time that it will take to do the translational work of, the needs of your workflow and your simulation and mapping that to a quantum computer, especially in a near term. So because of the time, because of the talent, and because of the IP potential, we think it's absolutely critical to get in now. And we think that 90% of the value in quantum computing will go to, like, say, 10% of users. We think that there's a lot of dynamics here that make it potentially a winner-takes-most kind of market in materials as well as others.
Maybe one thought to add to that. I'm fully buying into everything Matt just said. I would also think about it from the perspective of if there is a first demonstration of usefulness, people will jump on it. And most likely it's going to be, I don't know, maybe 2 or 3 different hardware players will reach that point in quick succession. But more likely than that is that there will be a first winner and then maybe a second winner a couple of months, years later or so.
Yes.
So if I don't know, if PsiQuantum or IBM or IonQ makes it, then only a fraction of the overall hardware is actually going to have the ability to be useful. So everybody's going to jump on that. And if you're then starting to think about quantum, you will more or less be at the end of a very, very long line that's going to form.
Because we're in France, it could also be Pascal or Alice and Bob as well.
Yeah. Great. Yeah. Okay, yeah, so we thought about the future, we talked about the limitations, I guess, and the timelines are uncertain, right? So I guess I don't want to ask the question of when do you think it will happen. I'd rather ask the question of what would be some early indicators that we're on the right path, we're essentially making progress, and it could serve as an alert, right? There's some milestone, maybe in 12 months, maybe in 24 months, that could serve as an alert that we're on the right track, and this was a key milestone that was just achieved, and therefore we might move forward with 2 or 3 more milestones and actually get there, right? So do you have a perspective on what some of these milestones might be?
Yeah, so I guess the very first sort of Sputnik moment of quantum computing, the first really important milestone was this achievement of quantum computational supremacy in 2019. And that was for a synthetic benchmark problem, and that had no relation to real world. It's a random circuit sampling problem. You can't do anything with the results, but you can just show you cannot simulate this machine anymore with classical compute. Then on the way between that and achieving practical quantum advantage in chemistry, there's a very natural sort of intermediate step, and that is achieving a quantum advantage in simulating quantum many-body systems that are of academic interest. So in academia, there are these toy models of materials that are of academic interest because you can study phase transitions and all sorts of properties that have nothing to do with like the properties of real materials, but they're sort of toy systems to understand what is happening in these systems. And they are a bit simpler to simulate than molecules because they have some translation invariance, for example. So that's something that's going to happen before, and that's going to be a very good milestone that should be a wake-up call for everyone who's like interested in the next phase.
Okay, very good. Thanks, Daniel, Matt. Any other milestones we should watch out for?
No, I think that's a good milestone. So whenever you read in the newspaper about a quantum computer solving a problem that doesn't sound like non-comprehensible if you don't have a physics, maybe master's, maybe even PhD, then this is probably a good indicator. I would also say that this is most likely going to be an individual demonstration where a hardware and a software partner will partner up. It's going to be a paper, not immediately a commercial grade platform solution. So that's, I would say, the biggest indicator. Yeah. And I also like the specific problem Christian selected.
So for me, I think the number one indicator from our purview would be the number of POCs out there, and then the number of POCs where they're using, hardware or where they're using a specific, materials platform that's quantum inspired or, quantum ready. That would be the most important thing, and would like to see that increase in the way that over the last 3 years, pharma increased after the Exscientia and the and the like other deep tech heroics during COVID. So I think that was a big thing there. The thing I would also like There's the kind of simulation size. I think that Christian was alluding to. The other thing I would love to see more materials science units within companies focus on a little bit is the speed of experimentation and measure KPIs associated with that. Some do, but in my view, accelerators on the speed of experimentation, including fast failures, I think is just a really, really good indicator of progress in the way that materials science units are thinking about innovation.
Okay, thanks. So maybe my last question would be: we have a lot of vendors here, hardware, software vendors, middleware vendors. What would be some of the things that you can maybe challenge them to do, or we can all think together that we should be doing to create more of an interest in this research and just essentially push the envelope forward? Is there something specific, or did we already cover it? Is there something that maybe we can challenge the vendors out there?
Yeah, I guess every theory paper on this subject is essentially a challenge for the hardware vendors, and that includes the research that we put out. I think, again, the talk by Clemens this morning puts it very nicely. Like, no, we have defined the problem. We have done the research estimates with the best methods that we know today. When now you know what the target is. Yeah, if you can improve over those methods, or if you can build hardware that can actually run this, then yeah, you know what the problem statement is. Just come to us.
Great. Yeah. I think he talked about something like quite a few gates there for current hardware, but yeah, I guess that's really the goal, right?
It's also a problem statement for the theorists and the quantum algorithm developers to sort of pinpoint sort of where the algorithms need to improve to bring these research estimates down, and then that hopefully guides the smartest minds to work on these problems.
Anything else that we can come up with that we can challenge the hardware or software vendors with?
I mean, I'm a chemist in a world of a lot of physicists, so and I used to finance my studies, my undergrad studies, as a science journalist. So I have to put out that the overall ecosystem needs to be better in communicating what quantum computing really is to the general public. And I think, I mean, there are some narratives which are cool, like talking about Schrödinger's cat, but making the leap from that weird, which is kind of, the message is more or less quantum computing is kind of weird, it's non-intuitive, but then making the bridge towards, okay, and this is what quantum physics can actually do in a process like material development or logistics optimization. I think there could do a better job in explaining that, essentially. And maybe dropping some of the narratives like quantum computers are going to replace classical chips, or maybe cut down a little bit on the wishful thinking and up the educational and the pedagogic explanations of quantum.
Thanks.
I like the idea that you mentioned, Daniel, and I'm actually not that surprised to have discovered that you did some science writing. It's evident. I think that connecting the kind of weirdness of Schrödinger's cat, et cetera, to the visionary nature of what could come of quantum computing, which is like, a credit card size, flexible solar panel that powers a whole neighborhood. And of course, that is like an enormous statement about hype. And this is like, deeply in like the philosophical physics of quantum computing. And then there's some small part of the chain that a quantum computer could do that a classical computer, theoretically at least, couldn't do. And like, making that connection, I think, both makes it, really concrete and really inspiring. And to be honest, a lot of that is what it takes to get funding at these, big companies for like speculative R&D. And I think that you've got to avoid hype, but you also can't have your feet completely on the ground, because the other side of hype really is enthusiasm, right? And I think that in order to create that enthusiasm, there does need to be a clear delineation, a straight line between what quantum computers can do and what the future could look like.
Great point. So I think we have maybe time for maybe two more questions from the audience.
There was a question back here. It's been answered. Any other questions? There's one over there.
Thank you for the talks. Michel Craig from Multiverse, and we are doing a tensor network, and tensor network is coming from quantum chemistry. condensed matter. What is your opinion about quantum-inspired solution like tensor network as an intermediate milestone to get before fault-tolerant quantum computing as a specialist?
Good, very good point. Yeah, tensor networks and quantum-inspired in general.
Yeah, so there are many different things that go under this name of quantum-inspired, so it's difficult to have a uniform opinion on all of them. But yes, I mean, things like tensor network algorithms, for example, they really are methods that are, I guess, already firmly established in the academic state-of-the-art in computational chemistry, but they're not really firmly established in the industrial state-of-the-art of computational chemistry. And yeah, we should always try to take advantage of the tools that are available today before we wait for the tools of tomorrow.
Great. Daniel?
Yeah, I mean, I'm always pro innovation, so having new tools that maybe even maybe not good for Kipu, which maybe are raising the bar that we need to cross to be really, really useful and differentiating. But I would say for industry and society, this is important. Again, it's hard to judge everything about quantum-inspired in a nutshell, but of course, question would be, I think there are two questions. One, is it useful? If so, go for it. I would say from my industry days, many people don't really care if it's quantum-inspired or quantum, more or less. On the flip side, question is, if it's not so differentiated, is it really a stepping stone, you know, in what I said earlier in terms of capability development? Could be, but it's needs to be evaluated on a case-by-case basis, I would say.
Yeah, very well said. The only thing I'd add is that, you know, you've seen the rise of some kind of intermediate technologies and it arises out of a need that you need to show progress, right, typically in any POC or an industry. So you've seen, for example, the approaches of like neutral atoms players that have become, very, very well publicized recently. I think likewise, you've seen advances in quantum-inspired, and in particular those that either have intrinsic value, like to speed up experimentation, or that are a stepping stone. To the extent that it's either of those things, I agree that it's all to the good and actually really a kind of sine qua non to get traction in the enterprise.